like W, which is equal to XYZ squared. You have a 3D object and you have a 4D object. That 4D object, I don't know how to imagine that 4-dimensional object, whatever that is. I know they have some intersection somewhere. Suppose the level surface for this 4D object is that this guy equals to the level surface of this 4D object can be calculated. Remember that we take the fourth variable and set it equals to a constant. XYZ squared equals to a constant like K. So my Z squared is K divided by XY, and Z is equal to plus minus K square root of K divided by square root of X. This object level surface of this 4-dimensional object has some intersection with this graph. We're going to take a look at this. Then you're interested in calculating the volume bounded by this cube and level surface, or that 4D object. What is the volume? So you know that we cannot visualize this 4-dimensional object. What we can do, we can just take a look at the level surfaces of this object. Well, some level surfaces of this object are similar to this. We plug in different values for our K. Take a look at your K. And then we try to graph, for example, Z equals to plus minus 1 divided by square root of XY and the rest of those curves. It gives us a visualization of this 4-dimensional object, some part of it that is visible to us as human beings. You might change this into, for example, 2 divided by square root of XY, or you might be interested in having a negative. If you plug in 1 for your K, you have positive, negative signs, and then you are intersecting this object with that cube that you have. And then you are interested in finding the volume bounded between the cube and this 4-dimensional object. This is what we're trying to calculate using our triple integral. Very well. So what are we trying to do? We're trying to intersect this 4-dimensional object with this cube and then find a volume bounded between that 4D object and this 3D object. So since we know how to use triple integrals, let us just set this up. Here we have 1, 2, 3. We have 3 variables, and then here we have the function in 4-dimensional space, which is x, y, z squared. X, y, z squared, then d. Again, since all of these boundaries are fixed numbers, it doesn't matter if you write the order in terms of x, in terms of y, in terms of z, or y, x, z, or z, x, y, and so on. These are all fixed boundaries, so we're allowed to use any order that we want. Let's just take the integral with respect to y, x, z. It's not important at all. Y, x, z. So my inner integral must have the boundary for y. Then the most inner integral has the boundary for x, y, x, and the outer integral has the boundary for z, 0, circle, 1, 1, 0 to 3. Okay. Inner integral with respect to y. So we have to take this integral with respect to y. This integral with respect to y. You have x, you have z squared. Well, the only thing that is important for us is y. The integral of y is a half y squared. So this is equal to more space. So 0 to 3 for z, and then 0 to 1 for x. And here I have a half y squared x z squared, and my y ranges between 0 to 2 dx dz. Okay, let's calculate this inner integral. Y is 2, so you get 4. Y is 0, is not important. This integral becomes 0 to 2, 0 to 1, and a half times. Here you have 4 minus 0 and x z squared dx dz. Dx dz. Okay, you can simplify this. You can write 2 outside the integral. 2 integral 0 to 2 for z. I'm sorry, 3. I keep changing this. And then x 0 to 1. And then here I have x z squared dx dz. Well, let us take an integral with respect to x. You have a half x squared, 2, 0, 3, a half x squared times z squared. X is bounded between 0 to 1. So it gives you just 1, and you end up with 2 times a half, which is 1, integral 0 to 3 z squared dz, this which is a third, z cubed 0 to 3, which is 9.